Welcome to the second lecture of Galaxies Fall 2025 at Stockholm University. In this one, we're going to go through galaxy morphology and classification based on their morphology, and we're going to also do a quick review of photometric terms such as flux, luminosity, and magnitudes. Today's lecture is going to be split up into three parts. In the first part, we are going to talk about flux, luminosity, magnitudes, and surface photometry. In the second part, we're going to dive into the morphology of galaxies and the Hubble tuning fork classification scheme and different galaxy types more broadly and more generally. And finally, in the third part, we're going to look at surface brightnesses and surface brightness profiles and what we can use them for in the grander scheme of things. But first, the short photometry primer. Measuring absolute fluxes is hard, particularly in older times when we didn't have electronic devices to measure them with, such as modern times CCDs. What is much easier is to compare the brightness of two objects. And that's basically the origin of the magnitude system that we still use to this day. In its original, most primitive incarnation, it was simply a matter of astronomers with the naked eye assigning a number to various stars based on how bright they seemed in the sky compared to each other. Today, we have a more quantitative and formal definition of magnitudes, where the magnitude difference of two objects, two stars, for example, is given as minus 2.5 times the log of the measured flux of these two. So as you can see, the magnitude system is fundamentally a logarithmic system, which is something that would seem natural given that the human eye is logarithmically sensitive to light, or at least approximately logarithmically sensitive to light. So the magnitude system sort of reflects how the human eye works. Now, the magnitude system is by definition, as you can see, a comparative way of measuring two things, but you can always define a magnitude 0 point, and with that 0 point, you can rewrite the first equation as the lower one down here, where the apparent magnitude of an object is the apparent magnitude of the 0 point, or your object of comparison, minus simply 2.5 times the logarithm of the object in question. We're free to choose which object we want to use as a 0 point or which number we want to choose as a 0 point. Traditionally, various bright stars in the sky have been used. And in certain branches of astronomy, people still use the Vega-based 0 point or Vega-based magnitude system, which simply, at any given wavelength, will compare the brightness of an object to the star Vega in the Milky Way, which is visible with the naked eye in the night sky and is actually one of the absolutely brightest stars on the night sky. Images of stars and galaxies are often obtained by integrating over a part of the spectrum. Observationally, we do this by using photometric filters. These are filters that only let through light in a particular given wavelength range. That way you can obtain light in different filters, compare the brightness inside these filters, and get an idea, for example, of the color of this object. We use these filters attached to a CCD telescope as it is set here. If you take a look at this figure, you can see a plot in the lower panel here, which shows the spectrum of what looks like an O or B star overlaid with a set of standard astronomical filters. It looks like the standard Johnson filters, where you can see that these have standard wavelength ranges and what I call sensitivity functions sensitivity function is the name of the curve that you see here, which basically describes how much light any filter will let through at which wavelength. And as you can see in the upper panel, exactly where these filters are centered and how wide they are is not random. What you see on the upper panel is the transparency curve, or you can say the light transmission curve of Earth's atmosphere. And if we start out in the ultraviolet, Earth's atmosphere is completely opaque. It blocks all ultraviolet radiation, or almost all ultraviolet radiation. And then we move into the visual range, the range that is visible to the human eye, which continues out to about 10,000 angstroms. An angstrom is 1/10 of a nanometer, and we use angstroms over nanometers simply out of convention because it gives nicer, prettier numbers to work with. And as you can see, the Earth's atmosphere is basically completely transparent in this entire wavelength range, which probably is why that is the wavelength range our eyes are sensitive to. But as we move out into the infrared region, you can see that there are more and more wavelength ranges where the atmosphere is actually not transparent anymore. And then there are these islands of transparency at various wavelength ranges. And as you can see, the photometric standard filters are designed so they fit with each one of these islands of transparency. The human eye actually works in a way that is very similar to how this works. I have here two figures where you see the standard photometric filters from before on the left side with a typical B-star spectrum overlaid. And to the right, you can see similar curves, not for photometric filters, but for the color-sensitive light receptor cells in the human eye. You can see there are 3 different of these cone cells, and you can see their sensitivity curves as they have been measured. And you can see that they look quite similar to the filters that we see on the left side, right? You can also see that there is a very strong overlap between the M and the L cones being sensitive mainly to green and red light, which I guess should give us a hint about why red and green is the most common kind of color blindness in the human eye. When we report fluxes and magnitudes and so on, it should always come with color information. And that is because if we take a look here again, you can see that this typical B star, if we wanted to measure that in the B filter and we wanted to measure it in the I filter, we would obtain very different magnitudes or very different fluxes, because any star or any astronomical object emits differently at different wavelengths. So just giving a magnitude or a flux of a star is incomplete information unless we also can report in which bandpass it has been measured, or at which wavelength, and over how large a wavelength range it has been measured. So magnitudes are, as you know, usually measured in a photometric filter. And if we measure a magnitude in the V band, for example, we denote it MV, or we can also do it MR or MI or MUV, depending on which filter we are measuring it in. There is sometimes a case for reporting the flux or a magnitude or the luminosity of an object in a great total across the entire range of all wavelengths. Because remember that even though the wavelength range might be more or less infinite, the total energy that comes out of an object is not. So you can give some kind of quite accurate assessment of the total output of an object, and we call this the bolometric flux or the bolometric luminosity. But such a number is often quite practical to use for, should we say, theoretical purposes or for modeling purposes, but they're not very practical to work with for observational purposes. So if you are an observational astronomer, you will not work with this bolometric flux or bolometric luminosity very often. As I hinted at in the last lecture, we often work with what we call a color index in astronomy. We use this in the color magnitude diagram, if you remember this. And the color magnitude diagram showed one index, which was, if I remember correctly, G minus I, but you can use any color index you want to. It is simply the difference in magnitude between two filters. And oftentimes we will use two adjacent filters, but you don't have to. Canonically, or as a standard, we use B minus V, that is the blue filter minus V, which stands for visual, but it's usually centered around green colors. But other filters can be used too, and often are. What the color index means is a little bit different. For stars, they often mainly encode information about the stellar temperature, whereas in galaxies, where you have the integrated light of a very large population of stars, that doesn't make much sense, but it does encode information about stellar ages and metallicities and dust content of a galaxy. Taking a look at the dust content, dust affects different wavelengths differently. So we can use what we call the color excess, or often called EB minus V. But you can, in principle, use other filters, again, a different color index to compute the color excess. But oftentimes we don't do that. Most of the time we don't do that. But you can use that as a measure of dust extinction. So when starlight passes through a cloud of gas that contains dust, light at shorter wavelength has a much higher probability of being absorbed by the dust grains than light at longer wavelengths, which means that you basically get a curve. You get a curve for the extinction that is done by dust to this light, which suppresses the spectrum of a star or a stellar population differently along the spectrum. When we look at fluxes, it is important to know about the inverse square law. For a source that is emitting its radiation isotropically, that is equally much in all directions, the measured flux density will be related to the source luminosity by the function that we see here. So what is the difference between density and luminosity? The luminosity is the complete output along all directions. So the total summed energy flux in a given wavelength range, but over all directions. On the other hand, the flux density is the amount of flux that we measure per area unit or per unit area. And as you can see, hopefully can see intuitively, if a star is emitting the same amount of radiation in all directions, but we are moving further away and measuring it with a detector of fixed area, then the further away we are from the star, the less of its flux we will receive on our detector. And that is exactly this dependence of the flux density, on luminosity, and on distance, the distance squared. This means, if we think about it, that if you double the distance, you get a quarter of the flux density. If you triple the distance, you get 1/9 of the flux density, and so on. The unit of measured flux, or actually flux density, is what we call Jansky per second per square meter, or more commonly in the CGS system that we also use, ergs per second per centimeter squared. Janskys and meters are often used in the radio astronomy community and in the infrared astronomy community, whereas the CGS system is more often used in the optical and UV astronomy community. But this is not a strict rule. This is just what people most often do. The absolute magnitude of an object is defined as the magnitude of a source as we would see it if we were measuring it from a distance of 10 parsec. So when we measure magnitudes as we saw them before, denoted by a little m, this is what we call the apparent magnitude. That is basically the magnitude as we measure it independently of how far the object is away. So the apparent magnitude, little m, is a measure of how much light we receive from the object. The absolute magnitude, on the other hand, big M, is a measure of how much light the object physically emits. And the way to convert from one to the other is by taking the distance into account because of the inverse square law from before. And the formula for that is, as we see here, that the absolute magnitude is the apparent magnitude minus 5 times the logarithm of the distance plus the number 5. And just like with apparent magnitudes, we also have a relative formulation of this formula, which goes to compare the absolute magnitude of two objects in terms of not their fluxes as it would be with the apparent magnitudes, but their absolute luminosities as it would be with absolute magnitudes. Again, because apparent magnitudes are an expression of measured flux in our detector, whereas the absolute magnitude is a measure of absolute emitted flux or absolute emitted luminosity from the object itself. Finally, we also have a term that we call the surface brightness. The surface brightness is defined as basically it's a measure of the flux per angular area of the object that we're looking at. So whereas the flux density was relative to the area of our detector, surface brightness is relative to the apparent angular area of the object that we're looking at. Surface brightness is an important term because you can have the same flux from a star, which is a point source, where all the flux comes from just one place, and a similar flux measured from a large galaxy where all the light that you get is smeared out over a large area on the sky. And even though you would receive the same flux from these two objects, they would be very differently looking in our detector. And in particular, a very low surface brightness object, such as a low surface brightness galaxy, will be a good deal more difficult to detect in our detectors than a point source of the same flux. Surface brightness can be measured when we are able to resolve astronomical objects, which we cannot do obviously with stars, but we can do with many galaxies. And surface brightness, which is an important thing to note, is independent of distance, which is almost true, but only almost true. When we get to cosmological distances, surface brightness actually is no longer independent of distance. There is this thing that is called surface brightness dimming, which stems from the fact that on large scale, the universe does not actually obey Euclidean geometry, but something that is a little bit more funky than that. One way we can use surface brightnesses and surface brightness profiles is, for example, by extrapolating surface brightness profiles that we have measured beyond our limit to how we can measure them in order to try to find an absolute size of a galaxy. Imagine we have a galaxy that has a higher surface brightness in the center, and then the surface brightness goes down as we move outwards. Now, at some point, we cannot detect the surface brightness anymore due to limitations in our instruments, but we know that there's still more stars on the outside of this limit. Now, if we measure a surface brightness profile, we can extrapolate this profile out beyond the limit for what we can see and still get an estimate of the absolute size, mass, and so on of this galaxy, despite the fact that we cannot actually measure it all the way out. This is one of the most important, but far from the only way to use surface brightnesses. This was the end of part 1 of this lecture. I will be looking forward to seeing you in part 2. Bye for now.